In section 8.4, we're going to look at hypothesis testing, but in this section, we're going to look at testing a claim about the standard deviation or variance. Pretty much, though, we're going to look at testing a claim about the standard deviation, which means we're going to be testing something about sigma, because we're going to be testing something for the population, sigma, and we'll want to say something using a sample. So again, we're going to do both methods of hypothesis testing. We'll do the p-values approach and we'll do rejection regions. The good news is when we do the p-values approach, we're going to do the same thing we did before. Nothing will be new. We'll start with stating the claim. We'll figure out where the claim lands, if it's going to be the H0 or the H1, depending on which symbol it has, if it has an equal to or not. Then the complement will be the one that we don't have. And then we'll always use the alternative hypothesis to determine whether or not we have a left-tailed, right-tailed, or two-tailed test. We'll sketch a graph. Be careful. We are so used to sketching a normal distribution graph that works for Z's and T's. Be careful when you are testing something for sigma. We're testing for sigma now. Well, you have to go back and think about what we did in Chapter 7 when we were making a confidence interval for sigma. What did we use? We used chi-squared. Same thing here. We're testing for sigma. We're going to use a chi-squared graph. Remember, the chi-squared graph is not symmetric. It starts always at 0. And is a skewed graph. It does go off all the way to infinity. And again, just like before, if we're going to use anything as an endpoint, we're going to use a 10 to the 99th, just like we did in Chapter 7. How are we going to find areas in a tail for the chi-squared graph? We're going to use something similar to what we did when we had the normal graph. We're going to use a chi-squared CDF. But we also have to be able to get a sample statistic, a test statistic, so that we can find our p-value. We're so used to our calculator doing this for us. It cannot do this for us now. So there's a formula. The formula for our test statistic, our chi-squared, that's our test statistic, will be chi-squared equals n minus 1. Remember, that's just a fancy way of saying your degrees of freedom. Times, we've got s squared. Well, s, remember, is your sample standard deviation, and that is squared. And on the bottom, we have a sigma squared. That's going to be what we think our population standard deviation is. All of this information has to be given in the problem. And again, we're only doing the chi-squared here, and we have a little bit more work because our claim is about the standard deviation in these problems. Our claim is about sigma. So what do we do once we have our test statistic chi-squared using this formula? Well, we are going to fill it in on our picture, whether it's a right-tailed, left-tailed, or two-tailed. So we're going to do our picture. Then we're going to use that chi-squared value or values to figure out what the p-value is. Remember, the p-value will be the area in the tail or tails given by your test statistic. Your p-value is the area in the tail, or if it's two-tailed, tails given by the test statistic. From our formula, we just talked about it. Okay. Well, if we're calculating an area on the left side, if it's a left-tailed test, it's pretty straightforward. We'll start at 0 and we'll end at whatever our test statistic is. If it's a right-tailed, well, then we'll use the right-tailed as our chi-squared, our test statistic, as the beginning of whatever our area is, and it continues on indefinitely. So on the right side, we use a 10 to the 99th. And we'd find the area by using a chi-squared CDF function. It works almost exactly like the normal CDF function that we're used to using in our calculator, except for it needs one extra piece of information. It needs your degrees of freedom. We're used to with the CDFs giving a start and a stop. We just need to give one more extra piece of information, which is your degrees of freedom. Remember, your degrees of freedom is just your sample size minus 1. So it can still find the area. And if it is two-tailed, we are lucky still. All you need to do is find the area in one tail and multiply it by 2. And again, once we have the area on the tails, this is going to be our p-value. Again, the area in the tail or tails given by the test statistic is going to be our p-value. Then we'll do exactly what we did before. We'll ask the same exact question. We'll say, is our p-value less than or equal to alpha? Same exact answers as before. If yes, we will reject H0. If no, we'll fail to reject H0. And then you have to figure out what does that mean about your original claim. And then write your fancy answer. Is there sufficient or insufficient evidence to either to either accept or reject your claim? Now we're also going to use